Okay, now, at this stage, essentially, we are coming to a part of our tutorials, which is going to be very, very important because all the things that we have done in the past, for example, we talked about the importance weights. We saw that, for example, how can we just have a distribution of them? And essentially, our model that we had for our Bayesian regression analysis on the woman data sets, we were able to essentially just use, I should say, fit that, smooth, I should say, those importance weights by the Pareto smooths importance samples them. Then at this stage that we are right now, we just want to do some kind of a diagnostics to see that the things which we have done from the past, how can we just have a good understanding of if they are good, if they are a good fit, or this is bad, we have to discard some of those values or not. But the thing which before we start, I have to just specify is that you remember that when we talked about the Pareto distribution, and as I just want to show that again on the things which we had on the whiteboard, the thing which is going to be very important for us when we just fit a Pareto distributions to our, I should say, importance weights, is that at the tail of the importance weights is that we see that, for example, make an inference of the best values, of the optimal values that it gives of the parameter shape or the shape parameter, which is going to be the alpha here, but at the R we have it at the at the loop package we had it called as a K parameter. We just want to see that which parameter of the shape is going to be the most optimal one. That's the purpose of our model that we were trying to just fit right now. Now, in order to do the diagnostics, you remember we just stopped at this point from the previous tutorial. We said that, for example, with the PSIS objects that we created on the woman data sets, we have a $sign and we have the diagnostics. If I execute that line, we see that we have two type of things that we get as part of the diagnostics. We have, I should say, we have a Pareto K, which is going to be the values of the shape parameter of the Pareto distribution that we talked earlier about that. You see that we have 15 parameters. You can essentially come here also to plot them. You say that, okay, I'm just going to plot PSIS, I should say for the woman. I'm just going to go ahead with the $sign, just go with the diagnostics, and I'm going to go ahead with, I should say, with the Pareto K. You see that it's the sequences of the information which I'm trying to extract from the PSIS object which I created before on the woman datasets. First one is the diagnostics, and the second one is the shape parameter, which is called K, which we have made an inference based on the things that we have here. It's going to be 15 ones. I'm going to plot it, and you see the plot which I create here. It's going to be the index we have on the horizontal axis. We have the index because you see that we have 15 weights which they have been smoothed from the fits which we did before. We have 15 weights. We have 1 here, we have 2 here, we have 3, we have 4, goes all the way to the 15 weights. And also as you see that, for example, the parameter which defines the shape of the Pareto distribution, which we call that the shape parameter, either we call that alpha in the some of the literatures, or we call them as K in the R environment. You see that the values of the parameter, shape parameter, it varies. It's a range from, I should say, between, I should say, you see that from the lifespan, we're just going to see that the exact value is going to be, let's say, for example, they had these values, for example, from 0.03, and it goes all the way up there, that it goes, let's say, something which is going to be above, a little bit marginally above 0.6. And now these are, I should say, the smoothed and the optimal shape parameters of the Pareto distribution, which our model from the PSIS has just computed it. You see a plot of it. The other thing which you just want to do, we have also the number of the effective samples which we had from the throws which we have. You see that, for example, for these ones, number of the effective samples, which we do not just want to focus on that. We are just focusing on the shape parameter that we talked about that. Also, in order to shoot some kind of a further diagnostics, we just want to do something which is going to be, I'm just going to go ahead with the function, which is going to be called, let me go ahead here to type this function, which is going to be the Pareto. You see that when you type Pareto, you have some values here. For example, for the first one, you can just come here and say the Pareto K-table. If you just go with the Pareto K-table and you just put the name of the object which you created with the PSIS on the woman datasets, you see that if you execute that line by pressing Control Enter, you will see that you have a table here which opens there. We have some kind of significant, I should say, values. Let's see, what do they mean? We have some intervals, some, I should say, signs that if something is good, bad, or very bad, and we have the number of the counts. You see that, first of all, it says that all Pareto K estimates are okay as long as the Pareto shape parameter of the Pareto shape is going to be less than 0.7. Let's see how. Let's go more into the details then. You see that if the interval, if you imagine as a shape parameter as a number, as a real number, if you come up with the shape parameter which is going to be from -infinity to 0.5, you see that which we have for our model, which is a woman data sets, which we did that, I should say, we just fitted that on by the stand GLM, which we have 14 K parameters, shape parameters in our Pareto distribution that fits our model. It says that you see that it's going to be essentially 14 parameters. You see that also from here. If you see the K parameter, the shape parameter, which is going to be here, let's say if this one is going to be 0.5, you see that we have 14 of these numbers, parameters, but the 15th one is a little bit above 0.6. However, if the parameter, the shape parameter, is going to be taken between 0.5 all the way to the, let's say, 0.7, which we have only one parameter, as you will see that on this plot, the one which is a little like an outlier at the top right corner of this plot, you see that this is still going to be okay. But if you have any, I should say, shape parameter of a Pareto distribution, which is going to be outside of that range, which is going to be bigger than 0.7 to the infinity, is going to be bad, and you will see that the model does not have any of those parameters in our model. Then we see that essentially the thing which we have for our Pareto K distribution, Pareto and the K shape parameter, we have collectively had 14 parameters, shape parameters, which, as you see on the plots also, which they produces, I should say, stability and guarantees, I should say, the finite variance of, I should say, are the models then, which we're just going to use that effectively when we just go to, let's say, for example, do have some kind of a predictive distribution in future then. Now, the other thing which I wanted to show that is going to be if, let's say, for example, if we have the Pareto, the other ones which we have, we talked about the table, and also, for example, we have the K value, which is going to be exactly the same thing, PSIS, it's going to be for the women, and it gives also the same values that we had. And you see that these are the values of the shape parameters that we extracted from our data sets. However, at this part of the tutorials, I think that's going to be a good point to stop this part of the tutorials, because we had a very good understanding of how can we just do a kind of a diagnostic phase on the models that we had. And also, for example, we can also, if you just want to get some more further information of, I should say, diagnostics, you can always just go to search on, let's say, for example, the Google, and you can just find on Stan Wignets that they have some kind of a description of how to just do some kind of a diagnostics on the shape parameters that we extracted. But essentially, you can just, the thing itself is a self-explanatory then. Then you just run, I should say, the Pareto table. And when you run, I should say, and you just put the name of the object which you created from the PSIS on your model can be anything. You can see that you have a good self-explanatory of the things that for what values of the shape parameter in your Pareto distribution you can expect to have a good results and stability and finite variance of your model then. Okay, on the next model, when we come back on the next tutorial, we're going to continue just go on to use these concepts for the model comparisons.